Hello, today we're going to look at oscillations. This is one of the shortest units on the AP test, and so while maybe not super important, it is something that's maybe not one of the most difficult parts, so these are some points that hopefully you can kind of collect without too much trouble. So there's two main types of oscillations. One is a spring, where you have something like a spring, and it's attached to a block here, and then it's going to oscillate back and forth. And so the force that you have pushing on it is going to be the spring force, and then it's going to store up potential energy as it goes over to the left, and then we'll have this maximum compression, and then it's going to move back to the right, and here we'll have most KE, so over here we have the most potential energy, and then it's going to move past that point, and then turn all back into potential energy. Remember, this point, the force is equal to 0, the spring force is equal to 0, because at that point x is 0, right? That's sort of our equilibrium point. And then at these points, the force is the maximum, so force is maximum, whereas the velocity is a minimum and actually equals 0, because it stops at that point and turns around. So that's the first point. That's what we have for spring oscillation. And then we also have pendulum. Okay, so springs and pendulums. And so a pendulum is just you have a string, it's attached to some kind of bob, pendulum bob, and then this is rotated out some small angle. One thing to note is that this is assumed to be a small angle. So something like definitely less than 20 and just a small angle, but that's just something to know. If you go farther in physics, you'll see why it's a small angle and learn sort of how to calculate it with a bigger angle. But for now, we're just dealing with smaller angles. And so we have sort of this shift here where it's kind of rotating. That was maybe not the most accurate, so it's a little bit shorter here, kind of rotating up here. And so same thing here, this is where we have the maximum potential energy. We have the maximum force, but the velocity is going to be equal to 0 at that point. Here at the bottom, we have velocity will be our maximum, and then the potential energy will be the minimum, and the force will equal 0 at that point. This is our equilibrium point. Equilibrium point, and then also our KE will be the max as well. One important thing with pendulums is sometimes you end up kind of getting a tricky trig question here. So if this is theta, we have something like this, and it says maybe like what's the change in potential energy, and what we need to kind of see is what's this change in height here. Okay, if this is L, both of those is L, and so what we need to do is we need to find out what this length is here, right? This length here, that blue length, is going to be part of the L length, and this blue length is going to equal L cosine theta, right? Because that's the adjacent side for this line right here, which is also L. And then if I want this H here, I'll just have H equals the total length, L minus L cosine theta. So that is one that's a bit tricky. That's something that you definitely could memorize, so that if that comes up, it's a little bit easier. But it's also possible if you just kind of remember the basic format and know how to solve it for yourself. You don't necessarily need to memorize that equation. But that is something that you need to be able to figure out. So we got our springs and we got our pendulums. So those are our two types of oscillations. And then we have a formula for each. So for our springs, we have Ts equals 2 pi root m over k. And then for our pendulums, Tp equals 2 pi root L over g. And you notice they look very similar, right? They're kind of in that same form with that 2 pi and a root of something over something. And then just kind of going through, this is our period. And so that is the amount of time it takes for one complete cycle. So for example, if I'm starting compressed over here at the left, I'll go to the middle, my equilibrium point, then go to the other maximum compression, and come back here, and then come back here. That would be one complete cycle. So all the way here, all the way back, one cycle. For a pendulum, same thing, starting from over here, coming all the way over here, and then rotating all the way back. That would be one complete cycle. Okay, so that would be our period. And then we just have the mass of the block. We have this spring constant. Okay, you'll notice in this the x the distance that is stretched does not actually affect the period of the pendulum. It will be moving faster, but because it's moving faster, the overall time does not actually change. Same thing for this one. You'll notice that the angle is not part of this. Remember that angle is a small angle, but you'll notice that it isn't actually part of this formula here. So once again, this L is the length of the thing, and then we the length of the pendulum right here, and then G, that is just 9.81, and so not too difficult there. Okay. Where it can get a little bit trickier is when we're looking at sort of the formula that we have, x equals x max cosine omega t plus phi. Okay, x max, this is the max distance. Okay, so in a spring, that would be the distance from the middle point to this maximum compression or pulling out part. Okay, and then we have cosine, and then we have omega. Remember, omega is just the angular velocity, which is our radians divided by our time. Okay, then we have the time, the current time, and then we have phi. So this is just sort of an offset. It says phase angle on the formula sheet. And so what this is doing is just saying, what happens if I don't start from this maximum point, right? Then it's not really going to be a true cosine graph where I'm starting from here, coming back up here, right? Like let's say I'm starting here, right? And so I just use this phase shift here to kind of represent that it's not starting at this maximum value, but it's starting somewhere else, okay? Oftentimes that part of the formula doesn't even necessarily come up. So not too big of a worry, but that's kind of why it's there. And same thing for the pendulum. Let's say I'm not starting at that maximum point, but I'm starting here, right? So I could pull it back to a certain angle and then give it a little push to give it that initial velocity, and then it will end up going to a higher maximum displacement. Remember, if, for example, we needed to find the velocity, we would just need to do dx dt. If we need to find acceleration, we do dv dt. So that's kind of just going back to calculus. So not too difficult with that formula even, which is probably the most difficult formula that you'd have. Now, the last part that we would want to talk about is graphs. So this is often something that comes up with these types of questions. They're going to give you a graph, maybe something that looks like this. They'll probably give you labels for everything. So this is maybe A, negative A, and then we'll say this is 2 seconds. Okay, and so you're looking at this graph, and maybe let's be something like find the length of the pendulum. Okay, and it feels like that's a really tricky question. I have this graph. How does that relate to the period of a pendulum, or how does that relate to the length? And so what you want to do is say, okay, I want to find the length. What formula do I have that has a length of a pendulum in it? Well, that's just Tp equals 2 pi root L divided by G. I'm trying to find this guy right here. And so I need to find that length. Now I know G, but the tricky part is that I don't currently know the period. The good thing, though, is if you look at the graph, you can figure out the period. And so that's a really important thing with any sort of oscillation type question, is that you need to be able to find the period in the graph. Okay, so that's really, when you're seeing a graph of oscillations, you're definitely looking for that period in the graph. Okay, so we know this is 2, and so you just have 2 equals 2 pi root L over 10, rounding G to 10, and you just solve for L, right? So not too tricky, but that's definitely something important to note, is that when you're seeing a graph for an oscillation, you're trying to look for that period and find that. And the reason I don't have too much to say on this particular topic is because any question you're solving almost always is another sort of unit that you need to use. So for example, maybe we're talking about energy, right? And so if I'm talking about energy, I just need to use my energy knowledge, my energy background, and use that to solve this question, even though it's about a pendulum or about an oscillating spring, right? Or it could be a forces question. Maybe it's asking about finding F net at a particular point, right? So for pendulums, you'd probably be looking at circular motion. For spring, you'd just be using a regular F net equals ma. And so in that case, once again, there's not a whole lot you're doing special about oscillations. It's really that you're just using forces, right? And so for that reason, I don't go too much into oscillations, but just kind of give you that background knowledge. It's generally pretty easy to pick up on when something is an oscillation question because you have something rotating, moving back and forth in a repeated manner, right? Pendulum or spring. So generally not too hard, but definitely important to note that you want to find the period in the graph. And then also just kind of knowing what these formulas are, right? So I have this formula for the position, which could turn into a velocity, and then I just have this basic formula for the period of both the spring and the pendulum. Okay, so that's oscillations. Remember, if you have any questions, make sure you ask them.